So today we're going to talk more fully about obtaining covariance matrices using I and J. We've demonstrated how to get a centering matrix Q, which is idempotent, using I and J matrices. We'll use this to show how to obtain a covariance matrix. So let's review first how to get a centering sums of squares and cross products matrix. So say we have raw scores. We've got 4 observation units and 3 variables. And I'll do our raw scores with a large X. And we have 3 variables and 4 observation scores, so it's going to be a 4 by 3 matrix. Alright. Now we can obtain deviation scores by subtracting the mean of each variable, and we talked about this in video 3.2, and it refers to this on page 90 of the text. So we actually have, I'm going to do the mean of these. The first variable, the mean is 6. The second one, the mean is 4. And the third one, the mean is 9. So if you add these up and then divide by the number of observations, which is 4, you will get this. So if we do it's large X minus the mean, so we'll just do 8 minus 6, 5 minus 4, 6 minus 9, and then do the next row, 7 minus 6, 4 minus 4, 11 minus 9, and the result is this: 2, 1, negative 3, 1, 0, negative 2, 0, 1, 1, negative 3, negative 2, 0, and like we did in video 3.2, we're going to label this small x. So we've obtained deviation scores from the raw scores here, and we can use this to get the centering sums of squares and cross products matrix, the CSSCP matrix. We know this from video 3.8, which is on, you can look on page 95 of your text. We know that from equation 3.1 that the centering sum of squares and cross products matrix is equal to the small x, the transpose, times small x. Okay, so we have, take this small x here, do the transpose. You get 2, 1, 0, negative 3 going across, 1, 0, 1, negative 2, negative 3, negative 2, 1, 0. This will be times our x, small x, of deviation scores. Okay. Using matrix multiplication, we find out that this is equal to 14, 8, negative 4, 8, 6, negative 2, negative 4, negative 2, and 14. Now keep in mind, just remember that the sums of squares are on the diagonals. So that's this 14, 6, and 14. And the sums of products are on the off diagonal. So we have 8, negative 4, and negative 2. Now with real data, this is a problem since deviation scores have rounding error. So if we had decimals, and multiplying deviation scores will compound the rounding error by squaring and multiplying it. So this is very simple, but it is prone to rounding error. We can calculate the centered sum of squares and cross products matrix by taking the raw sums of squares and cross products. Notice it's not centered matrix, which is large X, the transpose of large X, times large X, which is just our raw scores here. So this is not centered because it's created from deviation scores, and like I said, we can calculate the centered sum of squares in cross products matrix by taking the raw matrix and subtracting a matrix from it that corrects for the mean. And we'll actually do this with T and the transpose of M and get a more accurate result. So once again, this sums of squares and cross products matrix, which is X transpose times X, is not centered because it is not created from deviation scores. It's created from, as we see here, raw scores. Sorry if I may have missaid that before. So we actually should go back to chapter 2, and this is found in your text in pages 31 through 33 and equation 2.6, and you can look at that for further clarification. But I'm going to do this on this post-it here. So this transpose X is sums of squares raw because it's a raw data matrix. So this X, remember, is raw data matrix multiplied by its transpose. So this is sums of squares raw. We get deviation scores by subtracting the product of T and M from this, and we get sums of squares deviation is X transpose X minus T times M. Now you may be asking what this T times M is. T is the total. It's the sum of raw scores for the variables, or column sums. And M is the means of variables, or means of the column. So that's what we did up here. This is M, the means of the columns, or means of the variables. And T would be the total of these. Okay, so this Tm will actually create deviation scores because it corrects for the mean. So once again, we're taking this raw data and we're getting the deviation scores by taking this, a matrix of the totals of the sum of raw scores for the variables times a matrix of the means. So let's go back to a more accurate way of getting a centered sum of squares and cross products matrix. So what we can do is we have centered sum of squares and cross products equals X transpose X minus total and the transpose of the means. So remember, this is centered sums of squares and cross products. Excuse me, not centered, so this is the sum of squares and cross products. And this is what's going to center it. And you can find this as equation 3.2 in your text on page 106. So this is going to equal, we got 8, 7, 6, 3, 5, 4, 5, 2, 6, 11, 10, 9. And we know that from up here. I just took the transpose in order to multiply that by the raw data here. 7, 4, 11, 6, 5, 10, and 3, 2, 9. Okay, then let's do this part. We're going to subtract. This is actually going to be a vector 24, 16, 36, and then transpose of M, we get 6, 4, 9. So you might be wondering where these actually come from. So let's look at this raw data. Our total T is equal to 24, You add those up, you get 16, and add those up, and you get 36. Now, typically, because the total we demonstrated on that post-it, it's a capital T, which means a large matrix. But since this time we're only going to be doing just a vector, we represent it with small t. And we know that the mean is just going to be t divided by n, which is the number of observations, which is 4. We get our means to be 6, 4, 9, as I demonstrated up here. Okay, so let's simplify this. I'm going to bring it over here. What we get when we multiply these two, we get a matrix of the values of 158, 104, 212, 104, 70, 142, 212, 142, and 338. And once again, that comes from here. And then we subtract it by this combine. Remember, this is 3 by 1 and this is 1 by 3, so we'll get a 3 by 3. It's 144, 96, 216, 96, 64, 144, 216, 144, and 324. So this one comes from these two. Okay. We just subtract that out, and what do we get? We get 14, 8, negative 4, 8, 6, negative 2, negative 4, negative 2, 14. Look familiar? Yeah, it's the same thing that we got up here. So these are actually equivalent. Like we mentioned before, up here, this one is simple but prone to rounding error, this one. And this one is a bit more complex, but it's more precise. And certainly when we have decimals or not whole numbers in these matrices, that can become more apparent. However, there is a third alternative. Yay! So that third alternative is represented by equation 3.3, also on page 106, and that is this. The centered sum of squares and cross products matrix is the transpose of the raw data times the deviation scores that we got up here. Okay, so I'll demonstrate that. So here we'll have 8, 7, 6, 3, 5, 4, 5, 2, 6, 11, 10, 9. So essentially I have this piece of this equation and multiply that by our deviation scores here. 2, 1, negative 3, 0, negative 2, 0, 1, 1, negative 3, negative 2, 0. And lo and behold, that equals the same thing. Pretty cool, huh? So it's amazing how that works. It's very simple and it's precise. So it's basically taking the strengths of these two, simplicity and preciseness, and combining it through this one equation. And why does this work? Well, it works because the idempotent property of the centering matrix. So just as a note, the transpose of a product of two matrices is equal to the product of the transposes of the matrices in reverse order. What in the world am I saying? Basically, I'm saying this. The transpose of two matrices, A and B, is equal to the product of the transposes of the matrices in reverse order. So instead of A, B, we have B transpose times A transpose. Okay, so just keep that in mind. So we have the centering sums of squares and cross products matrix. We know from up here that it equals the transpose of the deviation scores times the deviation scores. And that equals, so we've got the centering matrix times the raw data and the transpose of that times the centering matrix and the raw data. So let's stop right there. How does that even work? How so? Let's demonstrate that. I'm going to use a different sheet of paper to talk about that. Alright, and we'll come back to that. So let's talk about that there. So we know that this is small x, our deviation scores, equals 2, 1, negative 3, 1, 0, 2, 0, 1, 1, negative 3, negative 2, 0, okay? We've already figured that out. So let's show that x equals the centering matrix times the raw scores. Let me go back here, okay? So we're trying to figure out, does this x, does it really equal the centering matrix times the raw data? Okay. So we know that the centering matrix times the raw data is the identity minus 1 over n times j. That would be times x. And that's what we got from the previous videos. So in this case, we know that n equals 4. That's the number of observations that we have. So let's take our centering matrix, Q, we know that is equal to the identity, so the identity is just 1s on the diagonals with 0s everywhere else. Minus 1 over 4, and is 4, times j, and j once again is just 1s, so we need a 4 by 4 j matrix. Okay, and this is going to equal you just multiply this through and we'll get 1/4 in each one. My hand's hurting now. And then you just subtract 1 minus 1/4 gives us 3/4. We actually know that that will be on each diagonal. And 0 minus 1/4 will give us negative 1/4. And I'll go ahead and write that through. Okay, so that's our centering matrix. So we need to multiply the raw data x by that. So centering matrix times x equals, and I won't write it out fully this time. I'm just going to show on the diagonals we've got 3/4, and everywhere else we have minus 1/4. And multiply that by x, which is 8, 5, 6, 7, 4, 11, 6, 5, 10, 3, 2, 9. And what do we get? You can go ahead and multiply that through. You can do it on using Excel or whatnot. What we actually get is 2, 1, negative 3, 1, 0, 2, 0, 1, 1, negative 3, negative 2, 0. Where have you seen that before? I'll give you a hint. I spy on this same page the same thing. Yeah, that actually equals our x that we have up here. So thus, x equals the centering matrix times the raw data matrix x. And as a matter of fact, x transpose does equal centering matrix times the raw data matrix x transpose of that. Okay, so I'll just slide this over. Let's make the connection. Let's see if you can see that there. Let me move this up. Okay, so we see using these two things that you can make the transition from this step to this step. So let's continue. We can further do this out. We get this here. Okay. And we know that because of this property, we can go to this next step. Then we can say transpose of that times the centering matrix times x. And we demonstrated this in video 3.17 that the centering matrix does equal its transpose because it's idempotent. Therefore, the transpose times the centering matrix will also equal this. So that's how you can go to that step. And that's, once again, because it is idempotent. And lastly, what do we get? Transpose of raw data times the deviation scores x, which we demonstrated here. And as we just did on that other paper, we know that we can go from here to here, as we demonstrated once again. Okay. So finally, we have a centered sum of the squares and cross products matrix, which we know is used to get a covariance matrix thanks to the idempotent nature of the centering matrix. So once again, we did get the centering matrix using I and j. That was then used down here so that we can figure out that the centered sum of the squares and cross products matrix does equal this. And once again, we can use that to get a covariance matrix, which all you really do that we've demonstrated before, you just divide by the degrees of freedom, or in other words, multiply by the inverse of the degrees of freedom. So this is crucial in getting a covariance matrix. I sure hope you had fun. I sure did. You have a good day.